Our team name is Denver and this is our video on Introduction to Geology and Soil Mechanics. The team members are Michael English, Aidan Hyland, Patrick Lucknan, Keane McNamara and Agmar Bryan. Our brief specified us to build a berm outside Thomond village to prevent it from flooding. It showed us where to get the soil from for the berm, and it also stated that the berm should retain water without major seepage or failure. In November-December of 2009, the water level actually rose over the river embankment and flooded Thomond village, which caused a lot of damage. What is the berm? A berm is a ridge made from earth, not allowing water to reach a contained piece of land. And here you see a cross-section of a typical berm. Examples of berms. There's loads of examples of berms, and they come in many different varieties and sizes. The biggest of berms retain millions of litres of water compared to the smallest of berms, which only retain tens of thousands of litres of water.
On week 3 of our comeback to you right after Christmas, we went on a site visit to Thomond village. This site here along the River Blackwater was where we were going to locate our soil to build the berm, and this is the site that we're actually going to build the berm on. The reason we went to the site was really to collect soil samples for testing, to check the various stratas of the soil and to check the depth of the water table. From this diagram here you can see that the topsoil is at a distance of 0.35 metres below ground level. The subsoil is at a distance of 0.72 metres. The clay was at a depth of 1.37, and after 10 minutes the water table was at a depth of 1.6 metres. And then as with the dig went on, we could see that the size of the excavation began to fall in and it became extremely dangerous.
One of the main reasons we carried out a trial pit was to obtain samples which we could then test on. We wanted to test our samples so we could characterise our soil. Some of the tests we carried out were cone penetration, water content, plasticity, sieve analysis, Proctor test and specific gravity. The way we carried these out, we carried out the cone penetration to allow us to get the liquid limit of the soil, sieve analysis to determine the clay silt fraction percentage. We actually used wet sieve analysis because we had fine soil particles in our sample. The Proctor test, which allowed us to determine the maximum dry density and the optimum water content. Once the soil is at its maximum dry density, it is at its highest strength. The analysis of the results then, we got our moisture content of the sample, which was 37%. Our liquid limit was obtained at 60%. Then from tables we could work out that our soil was of high plasticity. Our specific gravity was 2.6. For our sieve analysis, 99.7% of our soil was finer than 0.06 millimetres. And then on the next slide here you can see, using an A-line, we were able to categorize our soil as clay with high plasticity. Then once we graphed our results from our Proctor test, we could obtain the maximum dry density, which was 1.85, and our optimum water content, which is 13%. Then our liquid limit, which is the water content corresponding to a 20 mil penetration, which you can see here, 20 mil penetration, and the water content was 60% of this. These tests we carried out helped us to categorise our soil.
Some of the issues which had to be taken into account in designing our berm were the physical design of the berm, the seepage through the berm, the underground seepage and the erosion of the berm. There are many key design decisions which were made throughout the project, which were the height of the berm, the fill of the berm, the crest width of the berm, the slope of the berm downstream, the slope of the berm upstream, and the freeboard allowance and the installation of a drain in the berm. As you can see from our diagram, the slope of our downstream is 3:1 and the slope for upstream is 2:1. The height of our berm is 3 metres with a crest width of 3 metres and a freeboard allowance of 1 metre. The installation of the tow drain allows the seepage to exit the dam without causing any excessive erosion to the dam. And also, as you can see here, there's grass on the downstream slope of our dam, which also provides a counter reaction to erosion. Using our the height of our dam and our crest width, and our slopes of our downstream and upstream, we were able to calculate the angles which we need at our downstream and upstream, which were 18.43 degrees and 26.57 degrees.
Okay, I will go through the next few minutes about three main factors that influence our berm design: seepage, piping, and erosion. So, worth noting that our berm will have seepage despite its low permeability. Seepage is the seeping water through our berm. In order to counteract that, we introduce a toe drain at the end of the berm so that the water can flow safely out of the berm without it eroding. Seepage can only become a problem when there's a build-up of water in the berm, and that thus is eroding it. It is worth noting that the phreatic surface or the top flow line will always has to be on top, always has to be inside the berm. If this isn't inside the berm and it just flows out through here, it will erode the berm and lead ultimate failure. Another thing that we had also have to do was piping. Piping is when the unstable condition when the upward force of the seepage pressure exceeds the weight of the berm. In other words, if the upward force is greater than the downward force, that leads to an unstable condition and will result in the failure of the berm. But so how do we do this? What we did was we extended the berm downward to increase the flow lines, or the distance travelled by the flow lines. By increasing this we're thus decreasing our upward force. Also, we introduced filter sands over the far side. The reason why we did this was when the upward force is also going, it will create a void here if there's nothing acting on this. By introducing filter sands, we're filtering the water through, and we'll end up having no voids. Other things we could have done was we could have introduced piles or phreatic layers at the end to resist it. The final thing we're going to do is I'm going to talk about is erosion. Erosion, there's different ways erosion can happen. It can erode the downstream face, it can crack the jam due to piping in the berm, piping up underneath the berm, and animals can also have erosion in it. What we did was we introduced a grass cover here to resist berms, or resist erosion. But by introducing this grass cover, it helps compact the soil, and it also acts against frost.
The final part of our project is the post-construction health and safety plan. Fencing is a very important aspect as it is vital to keep livestock, people and vehicles off sensitive areas of the berm. This helps to maintain grass cover, it minimises erosion and it controls access to the berm area as seepage problems occur from tyre tracks or from animal tracks. Settlement is a very large issue in our project also. Most dams settle out in the first year after construction. Largest settlement occurs at the top of the berm as the mass is the highest acting down and the pressure is the greatest acting on the foundations. Settlement should always be taken into account during the design process and not left till the very end. The crest of the berm must always be horizontal, no low spots, as this can cause seepage problems. Overcompaction of the soil also creates cracks in the soil, and this can cause seepage problems, and this affects the settlement of the berm. Seepage and drainage is a very important issue, as all berms leak to a certain extent, as Aidan pointed out earlier. It is only a problem if it affects the embankment, which is the berm itself, the spillway, which is the cross section, or the outfall, which is at the very base. To prevent this, drains should be built during the construction and not after, so to relieve the water that's flowing through. Trees and bushes as well. They should never be allowed to grow if they have deep roots, as this can cause cracking in the soil, and this can protect against erosion and seepage problems, and it assists with the maintenance of the berm also. Animal activity is also a very important need that has to be prevented against, as constant inspections should take place to make sure that there are no mouths by termites or burrows by any sort of ground living animal. Here are some references from the project. I would like to thank you for watching.